In this week's lecture, I mentioned the heap memory. This is an area of memory where we can store arrays or other variables. But to allocate memory from the heap, we have to request it. And typically we do that using the function malloc, memory alloc. What you do is you pass in the number of bytes that you require, and it returns an address. And an address, of course, is stored in a pointer if we want to use pointer arithmetic. So in this code, what I am doing, I am asking the user to type in the number of megabytes I want to reserve. I multiply that by a constant to calculate that in bytes. I then request that memory. Now, the understanding is normally that malloc will reserve that memory for me and return the start address of that block of memory. So I check the address to make sure it's not null, and if it isn't, that means it was successful, or so it would seem. And then when we've finished with it, we must remember to free the memory up as well. So let's run this code, and I'm going to look at the same time as I step through it, the system monitor, and in particular the memory and swap history, where we see memory commits. Now we have physical memory here and swap memory, which is swapped out onto storage such as disk. So let's build and step through the code. So we click the debug symbol. It'll switch to the debug perspective. I'll say yes. And now I'm going to step line by line. So press F6. Now it's going to read the keyboard. How many megabytes? Well, let's throw caution to the wind and go for 1024, which is a gig. Now that's quite a lot of memory to request. So that's now there, and if we look at this variable, we see 1024. That's then multiplied by a constant to make it this rather large number, which is 1 gigabyte. Now I'm going to call malloc and see if it actually allocates it for me. And I want you to watch this trace as I do it to see if anything happens. So I press it now, and for some strange reason, nothing happens. Maybe it didn't work, so we'll check the pointer. Well, it looks like there's a pointer there, all right. That was successful. So I call free, and I finish with it. And what's strange, or may seem strange, is absolutely nothing happened here. It's as if we didn't allocate any memory at all. Well, actually, that is the case. I never used it. I didn't actually do anything with the memory. And the way Linux and other operating systems work is, well, if you don't use it, I'm not going to really allocate it. So memory is divided up in a physical sense into pages, and we talk about committing pages, actually reserving the real memory. Well, until you actually genuinely go and use it, it won't even bother. It does it what we call lazily. So let's actually try an experiment. Let's actually fill all the reserved memory with zeros, with a mem set. So that's the start address, that's the value to fill, and that's the address, the pointer for the beginning of the block that malloc gave to us. So now we're going to put our money where our mouth is, as we say sometimes, and actually write to this memory that we've requested, and we'll see if we've really got it. Have we really got 1 megabyte? Okay, so back to the C++ perspective, click build, everything seems fine. Okay, let's debug and step through. Now, yet again, watch the memory and swap history. These two pie charts as well are quite interesting. So let's step through it. And yes, I'm going to respond on the keyboard 1024. My 1 gigabyte again. Okay, now here comes malloc. No response. Seems to be successful. And now the moment of truth. Let's try and write into this memory. It takes a little while because something's happening. And we're through. And look at the memory commit. It suddenly leapt. A lot of physical memory has been used. Now this virtual machine has only been given a gig. So almost all of it's now been committed, but that's not enough. So some of it's been swapped out onto disk as well. So it's worked. Malloc has actually given me the memory I asked for, but only when I genuinely proved to the system that it was going to be used. So let's try a couple more experiments. Let's see what happens if we don't do free. Now, if I was to repeatedly call malloc, that would become disastrous. Let's get that clear up front. But what I'm going to do now is I'm going to kill the process off prematurely before we get to free. So in we go. Memory's come back to 0, notice. So there's a clue. 1024. Whoops. Step through. Let's actually write to the memory. Bang. Wait for it. There we go. Memory commit's gone up. Pages have been committed. And I'm going to hit stop. Plump. And with an operating system, when a process is killed, all the memory is released. So even if your process crashes, you shouldn't, in theory, leak any memory off the heap on Linux and other operating systems like it. Okay, one more experiment. What if I only write to, I don't know, a tenth of the memory? Will it still commit the whole lot? So, let's see what happens. Let's watch these two bars again. We're going to build and run. We'll actually just hit debug. That will do the same thing. We step through. I type in 1024. We step through. And now I'm going to write a tenth of it. And see this history here? Compare it with what's happened here. As you can see, it's not given me all the memory at all. And we can see the physical RAM hasn't been filled. And there's only a little bit swapped out. So it is pretty nimble. Yeah? If we free it, you see it should come back to ground level again. So heap managers are quite nimble. Even though you've called malloc and you've got an address back on a system like Linux, 1, it doesn't mean the memory's really been allocated yet. 2, doesn't guarantee it's actually been successful. If you go for very large amounts, you can get into problems where malloc returns an address and yet subsequent writes could fail. So don't be surprised when you look too closely. Heap managers are smart.